Okay, good morning. Welcome back to Mass 814, Algebraic Theory of Semigroups. Last time we are talking about regular semigroup. So if you can remember from the last discussion, we defined the notion of a regular semigroup. That a semigroup S is regular if for all elements A in S there is B in S such that A, B, A equal to A. In other words, we say that a semigroup is regular if every element of the semigroup is regular. And then we define the concept of rectangular band. We say a semigroup S is a rectangular band if for all AB in S, it happens that ABA is equal to X, A. So a rectangular band is a semigroup in which every element, this equation holds for any two element AB in the semigroup. So the notion of, by the very definition of a rectangular band, we immediately see that it is a regular semigroup. And you remember also from the last discussion, we defined what we call a band. A band is a semigroup of idempotent. So if all elements of the semigroup are idempotent, then that semigroup is called a band. You can still recall all these ones. Okay? So, but the difference between a regular semigroup and a rectangular band, we explained even in the last class, is that in the rectangular band, every element is regular. So therefore, every rectangular band is also a regular semigroup. But then, it happens in a way that every element is made regular with respect to every other element of the semigroup. So for every A, if you take any other B, ABA is also equal to what? A. Then you now say you have a rectangular band. But for a regular semigroup, if there exists just one element B, such that ABA equal to A, then you say it is regular. But for rectangular band, the equation must also hold for every B in the semigroup. So this is the situation between, the difference between a rectangular band and a regular semigroup. So which means every regular semigroup is a rectangular, every rectangular band is regular semigroup, but not conversely. We have regular semigroups that are not rectangular band. We started with a theorem in the last class characterizing this notion of rectangular band. And this theorem is this one, theorem 1.8. I think this is the correct label, 1.8. We say let S be a semigroup. So if you take a semigroup and you want to know whether this semigroup is a rectangular band, you can check any of the following three conditions. Okay? And once any of the following three conditions that I'm going to state are satisfied, then that semigroup is rectangular band. So it's like you don't have to always look at this equation being satisfied with respect to every other element of the semigroup. But you can check the conditions. Actually, these conditions will justify why the name rectangular band. Okay, so we will see this one. So then the following are equivalent conditions. Equivalent conditions of statements. So the first statement is to say that S is a rectangular band. To say S is a rectangular band, it means what we stated here is happening in the semigroup. That for every A and every B, A is equal to A. And it is the same as saying that each element in S is an idempotent. That is, every element of S is an idempotent. Did you remember what an idempotent is? Yeah, an idempotent is an element E such that E square is equal to E, whose square is equal to itself. And that for all A, B, C in S, the equation ABC equal to AC hold. So every element of the semigroup is acting as a middle identity. So anytime you see a product, you can always reduce the middle element. Actually, finding a product in this semigroup is a very easy exercise, in the sense that if I am to multiply A, B, C, D, E, F, the product is just AF. Just do away with the middle terms, and then you get the product. So you can reduce every product to just a product of two factors in this particular semigroup. So it has a very nice structure. Number 3, so once you check the semigroup and you found that every element is an idempotent, and every element is also behaving like a middle identity, then that semigroup must be a rectangular band. And you can now see why it is called band, why the term band is appearing in the name. Rectangular band, because band is a terminology referred to semigroup or idempotent. I hope it's okay. So you can see that every element is an idempotent from the second condition here. It means it's a band automatically. And then rectangular, this will be revealed in the fourth condition. The semigroup S should be isomorphic to L cross R, where L is a left zero semigroup, and R is a right zero semigroup. So you can find some left zero semigroup and a right zero semigroup such that your semigroup will be isomorphic to the direct product of the left and the right zero semigroup. So it's a right zero semigroup. So there is always some left zero semigroup and some right zero semigroup, such that you can do that. Maybe it's a left zero semigroup. Yeah. So it's a nice choice, we are not saying the choice of L and R is unique, but you can find this left zero semigroup, and you can also find this right zero semigroup, so that the direct product of the two will be isomorphic to the semigroup. So any semigroup that is the direct product of a left zero and a right zero semigroup is always a rectangular band. And if it is a rectangular band, it should also be a direct product of this kind of. So this is a complete characterization of the direct product or of the rectangular band. The third property is to say that the fourth, so this is the fourth property, is to say that So one can find, so there exists a semigroup A cross B, where A and B are non-empty sets with multiplication in here, and AB given by AB multiplied by CD equal to AD, such that S is isomorphic to this semigroup, this direct sum. So there exists a semigroup. There exists a semigroup of this form, A cross B, where A and B are just subsets, a non-empty set. So non-empty sets with multiplication given in this semigroup. Well, so you can see that multiplication, I'm not saying this A and B is a direct product, because direct product is given component wise. So if it is direct product, it should be A times B, A times C, and then B times what? D, if it is direct product. So, but we just see this as subset. You have two subsets, and then you take the Cartesian product of the two subsets and define a multiplication in this way. So we are claiming that with respect to this multiplication, this Cartesian product is a semigroup, and the semigroup defined in this way would be isomorphic to S. So if I can find some subset A and B, well, maybe subset of S, doesn't matter, or some sets A and B, so that the semigroup described with this product is isomorphic to S, then that's my semigroup S is rectangular band. I hope it's okay. So this is another way you can visualize a rectangular band. In fact, it is this fourth property that justifies the name rectangular in the naming of the semigroup, rectangular band. The reason why band is from the fact that every element is an idempotent, and then rectangular is from this. Because if you see this element of this semigroup as being element in the coordinates AB, and then you think of having CD here. Is it CD or A? A what? AD, and then we have CB, and we have the other element CD. So I'm thinking like placing the point in a square or rectangle. Well, I drew it as a square, but it can be a rectangle, it doesn't matter. So if you perform the product AB multiplied by CD, it should be equal to this one. Yeah, AD. Is that okay? And if you do the product the other way around, CD times AB should be equal to that element. So if you multiply element diagonally, you get the element in the other diagonal, in the other corner of the rectangle. I hope it's okay. So that is why it is called rectangular band. You elements are seen in the grid, partitioning of the coordinates, place where if you multiply elements from here, multiply by this, the result will be at the other edge or corner of the diagonal of the rectangle. I hope it's okay. So that is why it is called rectangular band, because this is the structure of the semigroup. Okay? We can prove this theorem. It's not difficult to prove. So how do you prove this kind of result? We say the following statements are equivalent. It means this if and only if this, and this if and only if this, and this if and only if that. These are all, any one of the two conditions will imply the others. So one can imply two, it can also imply three, one imply four, and two imply one, two imply three, three imply four, and so on. But then, if we can establish condition one implies condition two, and condition two implies what? Condition three, and then three implies four, and we also prove 4 implies 1, so it's a cycle now. So if you start from anywhere, you can get to anywhere else. I hope it's okay. So, and this is how we are going to go. So we prove 1 implies 2, 2 implies 3, and 3 implies 4, and 4 implies 1. And so all the 4 conditions are equivalent, because from any one of them you can get to the other. This is what we are going to prove. So let us start with 1 implies what? 2. So take note of the statement of the theorem, and then we prove it. So proof. So we are proving 1 implies 2. So suppose 1 hold, that is the semigroup is a rectangular band. I hope it's okay. So if we assume it is a rectangular band and take A to be an element in the semigroup, then, well, the first thing we want to show is that every element is an idempotent. So if I pick an arbitrarily taken A, it should be an idempotent. It means the square should be equal to itself. I hope it's okay. So for you to do that, you just square the element. If you eventually arrive at A, then it is an idempotent. I hope it's okay. So, but by the very definition of a rectangular band, that if I have A square and A square with something in the middle, whatever you take from the semigroup and put in the middle, you still get A square. So you can write this like this. I hope it's okay. But this is equal to, or can I put it here? This will be equal to, well, by associativity, I can write it like this, but that is equal to A square. You know, for all AB, whenever you have a product, the first element is the same thing as the last element in the product. The middle will just like the result will be equal to the element. This is by the definition of what? Rectangular band. So by definition of rectangular band, this is A. This in bracket is just A, which is A times A square, but this is still A, which is still A. I hope it's okay. So every A square is equal to A, meaning A is an idempotent. Okay? A is an idempotent. So every element of the semigroup is an idempotent. That is the first part of the second condition, second statement. Next, we show that for all AB, so next, for all ABC in the semigroup, we have, so what do we have? If you multiply ABC, you should get AC, so that B is acting like a middle identity. So, but this is the same thing as AB, so it will be AB Um, well, so we want to get AC. Maybe I should do it the other way around. Will be more easier to arrive at. I will start with AC and arrive at ABC. Okay? And try to arrive at ABC. So if you start with AC, then you can now see that AC is the same thing as A, B, A, B, A, C. Okay. Yeah, you can write like this. It's okay. Why? Because
we are in favor of A is equal as AB.
is it okay to do like this?
Yes, sir.
What do you do? What do you use here?
We use the since it's a we know that any A is equal as AB.
So A is ABA.
Yes.
Okay, good. But then, okay, so it's actually like this. For the A. And then C is also CBC for the C. Is that okay? But then we have ABACBC. Yeah, and you can look at this as a single element and then use the regularity condition to reduce this to B again. Is that okay? So this is ABC. So every ABC is equal to AC. And so therefore every element is actually like the middle identity. So this establishes the second condition. Okay? So now, what if we assume the second condition and try to prove the third one? So suppose 2 is holding and then we want to prove the third condition. So we are assuming every element is an idempotent and that ABC is also equal to AC throughout the semigroup. And then we want to prove what? That there is some left zero semigroup and some right zero semigroup so that our semigroup is isomorphic to the direct products LR. So here we will let L be equal to, so we pick a fixed element. We start with a fixed element. So we take C to be a fixed element of S. Well, arbitrarily taken but fixed. You can just choose any element of the semigroup. It doesn't matter which one. I hope it's okay. There must be something inside. It's a semigroup. It's not empty. I hope it's okay. So once you do that, you let L to be equal to SC and R, do I say like this? So maybe full stop and then let L be equal to this and R be equal to CS. Okay? You understand what this is? I'm talking about the set of all SC such that S is in S. Kind of right coset. Okay? And this is the set of all CS such that S is in S. But mind you, I'm not adjoining identity. So it's not actually, I'm not saying the principal left ideal generated by, or the principal right ideal. I'm not saying that. I hope it's okay. Okay? Then, for all, for any x, if you take an element x here, it must be SC and Y equal to maybe TC in L, because every element in L is some element of S times C. So I pick some element X and Y. We have that XY is equal to, so this will be SC times TC. Yeah.
Is the X, Y, and T, where are they coming from? X, Y, and T. Those where are they coming from?
XY?
X, Y, and T.
Yeah, they are picking elements arbitrarily from L. Choose any element from L. I want to show that L is, the product in L is closed and that it is also a left zero semigroup. That is what I want to show. So if you want to show that it's a left zero semigroup, you take any two elements from here. You see, you don't have problem with closure because anytime you take an element here, it is SC and the second element is TC, which is always what? SCTC. So it's always a product of some element in S and the C. So closure is always guaranteed. Are you following? You don't have problem with that. But what we want to show is that it's a left zero semigroup. And we will also show that this is a right zero semigroup. Is that okay? So to see that it is a left zero semigroup L, you take two elements, X and Y. And then you multiply X with Y. If this is equal to X, it means anytime you multiply in L, you get the leftmost element. And this is the nature of product in what? In a left zero semigroup. I hope it's okay. So this is what I'm trying to do. But what is this now? This is equal to, let me write it down here. So XY is equal to, well, SC. So you understand why I pick SC? Because it is coming from L. And the nature of things from L is what? SC. And the second one is also some element T. So maybe you should say for some S and T in S. Is that okay? Just for clarity. So T and then TC. But this is equal to SCTC. Yeah. Is that okay? No. Maybe it's like this. C T. I should see it like this. Yeah, but then I will use condition 2. Condition 2 says A, B, C equal to AC. So if I have something with something in the middle and the other thing, it should be the first and the last. I hope it's okay. So this is SC. But what is SC? It is X. So anytime you multiply in L, you get the leftmost element. So L is a left zero semigroup. Okay? And so L is a left zero semigroup. I don't know whether you are okay with this. Do I have to do this? Yeah, because it's the same. Okay? So I can say similarly, R is a right zero semigroup. Yeah, the same thing. You just be dealing with C from the right instead of C from the left. Oh, it's okay. So this is from the left. I mean C from the left. So if you choose X and Y from here, it should be CS and CT. And then you see the situation is the same. So next, we have to show what? Yeah, we have a left zero and a right zero semigroup. And once you have two semigroup, you can always define the Cartesian product. Well, the direct product, not Cartesian product. Okay? So now, we want to show that S is isomorphic to that direct product of L and S. So define the map theta from S into L cross R, where L cross R is actually the direct product by theta of S is equal to, so if you take S here, you map it where? Inside L cross R. But L cross R is the set of ordered pairs. So, ordered pairs. What is the most natural thing to do? They look like what? CS. So it is that's SC, I mean. And these elements, they look like CS. So I will take to that CS. That's the most natural way to do this mapping. If anybody asks you to map from S into this direct product, this is the most natural way to do it. In fact, the first thing that comes to your mind is to define theta in this way. I hope it's okay. We don't have any issue showing that theta is well defined. Well defined, yes. Because well defined because of the fact that binary operation is well defined. I hope it's okay. There is no way S will map to two different images because this product is unique inside L, and that product is also unique inside what? R. So binary operation originally is well defined in the semigroup S, and so therefore this theta is well defined. So we now see that theta is 1, 1. Theta is 1 to 1, meaning an injection. You know, we have to show that it is 1 to 1, an onto, and it is a homomorphism. Homomorphism. I hope it's okay. So I start with 1 to 1. So if you want to see that theta is 1 to 1, you do what? You assume two elements. Since if theta t or theta s is equal to theta t for some s and t in S, then what does this mean? This means SC, CS is equal to is equal to what? TC, CT. Yeah, because that is how we define theta. Is that okay? Yeah. So, but then, so we use condition 2 by S is S square, because condition 2 says every element is an idempotent. So S square can now be written as S C S. Still using condition 2, because condition 2 says every element is acting as a middle identity. So if you have SCS, it is S times S, which is S square, and that is S. I hope it's okay. But this is equal to SC. You see, the way you equate ordered pairs, SC must be equal to TC. So SC here is the same thing as TC. S. And again, well, which is T, CS. And again, CS is equal to CT. which is equal to, so I'll come down here, TCT. By using condition 2, C acting like the middle identity, this will be T square, but that is T. So whenever theta S equal to theta T, S is equal to T. That is 1 to 1 already. So the map is 1 to 1. So we have established this. Is it on to? The mapping theta is onto, since so what do we mean by onto? Every pair we pick from here must be an image. So if you take any pair here, there must be something coming down to it. So if you take any pair there, since for every S, well, it is true that SC, so for all SCCS, actually, maybe we can decide, we have to look at, we say SC comma CT. You see, this direct product, it mustn't have to, we are not saying all the elements are this diagonal. I hope it's okay. But it's just taking pairs, first entry from L, second entry from. So we are not saying all the elements are of the form, all the elements here are of the form CS, SC and CS. I hope you are following.
Yes.
So arbitrarily taking element is like this from that ordered direct product. Okay? So if you pick any element from the direct product, you should be able to produce some element in S that will map to it. Okay? So if we take any element in L cross R, then that element can be seen to be an image of what? So it is the same thing as so STC, you see we use condition 2. STC is equal to SC by condition 2. T will act as the middle identity. And again, CST. So I can write like this using condition 2. But this is what? This is the image of ST. This theta of ST. So it's the product ST that will map to this element. So every element in L cross R is an image. So theta is on. I hope it's okay. Okay? To see that theta is a morphism well, take what? We take two elements, S and T, from the semigroup, and then try to compute ST. Yeah, but we have, so what is this now? Yeah, it is going to be STC CST, but that is equal to this is going to be, so here we use the condition, we still use condition 2. Okay? to express this as what? SC.
So T will be B and
So we can see SCTC. So ST is SCT. Is that okay? Using condition 2 still. And then C, this is still what? SCT. And then associativity, we are using associativity without even referring. So this is SC, TC, CS, CT. That is how you multiply multiplication in the direct product. It's component wise. So this is clearly the product SC, CS multiplied by TC, CT. And that is theta of S, theta of T. So the map is a homomorphism. It's a morphism. Morphism. Yeah. So, yeah, it's a morphism. It's okay, I think. So morphism is you remember in our 801 class, in a category we say arrows are called morphisms. This is the same terminology we are using. We are using the categorical term for homomorphisms as morphisms. Okay? So this is it. And this is the end of the proof. Because this has already shown that what? S is isomorphic to that. If you have a 1, 1 and onto morphism from a semigroup to the other, then you have an isomorphism. So S is isomorphic to L cross R. Okay? Oh, well, we are not done yet. We still have condition 3 imply 4. So we still have to prove 3 imply what? 4. So suppose 3, what is 3 that this thing is happening? So we are assuming already that there is this left 0 semigroup and the right 0 semigroup such that S is isomorphic to that. And then we want to show that S is isomorphic to a semigroup A cross B in which what? In which what? The product is defined that way, in the diagonal product. So this is how we are going to do now. So so we suppose so here we are this assumption, this is what we are assuming. We are assuming 3 is holding. And then you know how we constructed this L and R. Okay? So since this is a left 0 and this is a right 0, so we can now say we choose A to be equal to L and B to be equal to R. It doesn't matter. Since we have them already, L and R. The only thing is that we will have to show that we can redefine the product. Okay? And then so if we choose A to be equal to L and B to be equal to R, and observe that the product in here, if you take 2 elements, that for all A, B, and C, D in what? In A cross B. the product is given by, if you take AB multiply CD, well, this is LR. A is actually, and if you are in the direct product, so you see this as the direct what? Product. So this is a direct product. Product is defined component wise. So this will be AC and what? BD. Yeah, but then this is happening in a left zero semigroup. So this will be what? A. And this is in a right zero semigroup. So this will be D as required. This is the required product. And hence, we have S isomorphic to A cross B. And here, product is defined like that. Yeah, because it's already, by 3, it's already isomorphic to L cross R. And this A and B are, so we just use L and R as our candidates for the sets A and B. And with the fact that L is a left zero semigroup and R is a right zero semigroup, this product is already happening the way we wanted it to happen for condition 4. I hope it's okay.
Yes,
So we now prove 4 implying 1. And that will be the final thing to do for the proof. So So 4 implies 1. And what is that? So suppose we have this, we are assuming that the semigroup is isomorphic to a semigroup which is the Cartesian product of A and B, where multiplication is defined in this way. Okay? And then we want to prove that our semigroup is what? It's a rectangular band. Meaning if we take any two elements. So if we have the isomorphism, so let theta from S to A cross B be the, or an isomorphism between them, because we are assuming they are isomorphic. So we must have an isomorphism. Now, so for any AB in S, let us assume, or let me use S and T, okay, and let theta of A of S to be equal to this ordered pair A comma B, and theta of T to be the other ordered pair C comma D. Okay, then yeah, ST, well, what do we want to show? It's a rectangular one. So we want to show that STS is equal to S. STS is equal to S. That is what we want to show. STS equal to S. So we compute theta STS. This should be equal to, since it is a homomorphism, so I can now push theta inside. This is preserving the composition. So this should be theta S, theta T, theta what? S. And that is equal to, so what is this? It is AB, and that is what? CD, and that is A, AB. Is that B? Okay. But the product is defined in this way. Product is defined in that way by the assumption of condition 4. And then you have AB. And that is still what? AB. But AB is theta S. And since theta is 1 to 1, we conclude that STS is equal to S. Because theta is 1 to 1. So this implies theta STS is equal to theta S. It means STS is equal to S. So therefore, the semigroup is a rectangular band. This is the end of the proof. Okay? So this theorem is actually proved in this way. It has suggested many different ways of looking at a rectangular band. And actually, this theorem is not available. There is no analogous of this theorem available in group theory. This is one of the results that reveals the beauty of semigroup theory. Understand that there are semigroups that behave entirely different from group. Okay? So I think, do we still have some time? Okay, we can start talking about monogenic semigroup. So, monogenic semigroup. So something that is very basic in group theory is the fact that if you take two subgroups and intersect them, the intersection is always what? Also a subgroup. It is not empty and it is a subgroup. But in semigroup, intersection of two semigroup is not necessarily a sub-semigroup. Why? Okay, let me give you an example. If you take the semigroup of natural numbers with respect to multiplication, and you think of all even natural numbers, if you multiply any two even natural numbers, it's still a natural number. How about odd? If you multiply two odd, you still get odd. So the collection of all even natural numbers is a sub-semigroup, and that of all odd numbers is also a sub-semigroup. What is the intersection? It's empty. So cannot be a sub-semigroup, because a sub-semigroup must be a non-empty set. So intersection of two sub-semigroup may be empty. It may be empty. It may not be empty. If it is not empty, then it is a sub-semigroup. But if it is empty, it's not a sub-semigroup. So you have to check that the intersection is not empty. But whenever it is not empty, it's not empty or not, you have to check whether it is not empty or not before you conclude that the intersection is always a sub-semigroup. So not always. There are situations where the intersection may be empty. Okay? So, so in a semigroup, the intersection, let me call it S. The intersection of any index family, a family. We take a family, maybe alpha from some index set. We take any family of sub-semigroups. Of S. If not empty, if it is empty, it's not a sub-semigroup. So if not empty, is always a sub-semigroup. Yeah. If it is not empty, it's always a sub-semigroup. But there is a situation we can look at where the intersection is always not empty. You can look for a particular family where you are certain that the intersection is not empty. You can do that. How do you do that? That is, you take a family of such semigroup of a special kind. For example, saying that you want to take a family of such semigroup where this portion of the semigroup must always be present. Something like that. That is, you identify a subset. Now, and so therefore it means if A is a subset, non-empty subset, of the semigroup S, if A is a non-empty subset of S, then the intersection of a family of sub-semigroup or any family of sub-semigroup so let me call it still T alpha, doesn't matter. The intersection of any family T alpha of sub-semigroups of S, this time around containing A. Since it is not empty, since it's always not empty, it's also a sub-semigroup. Yeah, why are we saying since it is always not empty? A is always present there. You take this set, contain A in it, this one also containing A. The intersection must also contain A. A has become a common element, a common factor of all of them. So therefore, A is always present there in the intersection. But this intersection has one extra property. Apart from containing A, which other extra property it has? It is the smallest of all of them. In fact, it's already a member of the family. So if you are talking about the family of all of them, if you take the set of the collection of all the sub-semigroup containing what? A, all of them. The smallest of all of them will be inside there because it is also a sub-semigroup also containing it. And it must be the intersection of all of them. Why? Because the intersection is always the smallest of any given collection of sets. Yeah. If you take two sets A and B and take the intersection is smaller than both of them. Always. Are you following? Are you following? So therefore, this intersection, it contains A and it's the smallest of all of them. So it is the smallest sub-semigroup containing A. Okay? It is, yeah, greater or equal to, yeah, greater or equal to. He is talking about when I mentioned that if you take intersection of two sets, the intersection is smaller than both of them. Now he is saying smaller or equal to, yeah, I agree with him. Because if A is contained in B, A intersection B will be equal to A. So intersection is always contained in both of them. So it is at least smaller than all of them. So this is what we have. Now this intersection is always a sub-semigroup, and it is the smallest sub-semigroup of S containing A. The smallest sub-semigroup of S containing A. You see, this is already identified. I mean, you cannot have two smallest. It's only one. It's unique. If you are talking about smallest of something, it's just one of it. I hope it's okay. So, which means we can give it a name in terms of A. Because if you change the choice of A, this smallest sub-semigroup containing A will change. I hope it's okay. So it is the smallest sub-semigroup of S containing A, donated by what? By A, like this. And called, it has a name. That sub-semigroup has a name. What is the name? Yeah, we call it the sub-semigroup of S generated by A. The sub-semigroup of S generated by what? By A. So how do you get it? That's the name. The sub-semigroup of S generated by A. How do you get it? This is how it is defined. You understood how to get it. It means what? I will find the collection of all the sub-semigroup of a semigroup. Inside that collection, I will look for those that contain A. You know, always that family is not empty. Why? Yeah, it contains A, and there has to be a sub-semigroup containing A always, namely the semigroup itself, because that A is a subset of the semigroup. So the entire semigroup is a member there. So that collection I know is empty. At least one is present there. I hope it's okay. So I can take all of them, so you get them where A belong. And now you have the collection of all of them, and then you look inside and see the smallest of all of them. Or you take the intersection of all of them. That intersection is always the smallest. In fact, always the smallest is among them. But this is not practically possible. Okay? In practice, you cannot always do this. Why? You can't say you are looking for all the sub-semigroups. That number may be very large. You cannot be able to exhaust it. I hope it's okay. So you must look for an alternative to this definition, because this definition is not useful in application. I hope you are following. If I ask you to find the sub-semigroup generated by these subsets, can you find that? Like in the semigroup of natural numbers, and I pick 3 elements, 1, 2, 3, 4, and I say find the sub-semigroup generated by 1, 2, 3, 4. What would be that sub-semigroup? Which means you look for all the sub-semigroup of the semigroup of natural numbers, and all those that contain 1, 2, 3, 4, and then the smallest of all of them, or you intersect all of them. That is a very huge task. So we get a characterization, and we present this as a theorem. So the sub-semigroup, is it time already? So maybe we stop here. From the next class, we take a break and come back. Okay? And then when we come back, we start from there. So we are going to just prove the necessary and a characterization for this sub-semigroup generated by A. Actually, it's not a difficult characterization. It's just to see that this sub-semigroup is the element inside are precisely all elements of S that can be written as finite product of members from the subset A. So we'll prove it in the next class. Thank you very much. After the break.